Hi everyone, this is Janelle Klein, founder of Open Mastery and creator of Open Mastery Learning Framework. So on the website, I've been talking about this iterative roadmap for embedded mastery. And so first I wanted to give you a high-level overview of what all this is about so you can decide if this is something that you want to be a part of. So first of all, what's the problem we're trying to solve? Why should you care about anything I have to say? So across the industry, you see this pattern where every few years we end up rewriting our software over and over again after driving one project after another into the ground. So why is this happening? We always start with the best of intentions. We're going to write high quality code that's low in technical debt, easy to maintain, and of course it's got to have good code coverage. And then this happens. We've got this business pressure and urgency to deliver features as fast as we can, and things just start to unravel. So things start off okay, but our problems are invisible. They're hard to measure, hard to explain, and there's a lot of features to deliver in not much time. So we bring up our concerns to the product owner, but they're like, we've got more important things to do. So then we keep deferring the problems. And as the problems grow, our releases start to get painful and chaotic. And we'll be down to the wire and the software will be broken. So we start working late nights and weekends trying to get the software back into a shippable state. And then we start relying on all these high-risk heroics to keep saving the day. But instead of our management seeing all this chaos as evidence of the problems, we're congratulated for the all-nighters and our great teamwork. Good job, everyone. Keep up that great work ethic. And as the problems grow even further, productivity starts to slow to a crawl. So the builds will be breaking, environments are going down, and nothing gets done without pain. So we start pleading with our management to give us time to fix all these problems, but now we're even further behind on our commitments. So management's in a panic. We need to go faster. Let's hire more developers. So now we've got developers breaking things because they don't know the software. And it's a full-time job just to keep the project from falling apart. And eventually exhaustion sets in, and that's the tipping point for project meltdown. There's usually one last-ditch effort by the team to turn things around, but if management says no and the team loses hope, it's the final nail in the coffin and the developers just start leaving in droves. I give up. I don't care anymore if the project fails. And most projects will never recover. So what's wrong with our current strategy? I mean, it's not like we don't know it's important to write maintainable code. So I was reading this book, Good Strategy, Bad Strategy, and by the first chapter, I already had my answer. A description of the goal is not a strategy. And if you think about it, this is really our strategy for success. We talk a lot about what it means to have maintainable code and why it's important, but what we don't talk about is how the hell we're supposed to pull this off in the context of a business system. The problem is we don't really have a strategy for solving this problem, and we really need one. So Rumelt says, a good strategy is a specific and coherent response to an approach for overcoming the obstacles to progress. So I started thinking about what are the biggest obstacles that prevent us from breaking the rewrite cycle? And a friend of mine drew this picture on a napkin, and I thought this just captured the problem perfectly. Managers and developers might as well be speaking different languages. So managers struggle with a lack of visibility. They don't understand what's happening on their software project, and they're afraid of making decisions that'll make things worse. Meanwhile, developers struggle with a lack of control, and they don't know how to explain their problems to their managers or influence this giant machine that's driving their software project into the ground. And so we get into this state of organizational deadlock where everyone is essentially waiting for a resource they don't have. And even when everybody knows the project is headed for a wall, nothing changes. And you see this pattern over and over again across the industry. The biggest cause of failure in our industry is this. This is the obstacle that we need a strategy to overcome. And this isn't an engineering problem, it's an organizational problem. So what's the strategy for solving these problems? How do we start working together and learning together as an organization? Well, we make the pain visible, something measurable, explainable, and something we can account for explicitly in our decisions. So how do we do that? Well, about 8 years ago, I was working on this process control system for semiconductor manufacturing. And we had this awesome team. We were disciplined with best practices, constantly working on improvements. But despite all these things, I watched the project hit a wall. And by hit a wall, I mean we brought down production 3 times in a row and didn't ship again for another year. So I thought the main obstacle was technical debt that was building up in the code base and causing us to make mistakes. So I wrote this tool that could detect high-risk changes to the code and then let us know where we needed to do extra testing. But what I found wasn't what I expected at all. Most of our mistakes were actually in the most well-written parts of the code. The bugs weren't in the crufty code, they were in the code that was written by our most senior engineers. And I did find one correlation in the data though. We made significantly more mistakes in the code that we didn't write ourselves. And while that made some sense, I mean, a lack of familiarity increasing the likelihood of mistakes, I couldn't help but think there had to be more to the story. I mean, this is what I knew. When I had to work with complex code, it was really painful. But what made development actually feel painful? So I started keeping track of my painful interaction with the code and visualizing it on a timeline like this. So the pain started when I ran into some unexpected behavior and ended when the problem was resolved. So that's 5 hours and 18 minutes of troubleshooting. So most everyone can agree that's pretty painful. So the amount of pain was driven by 2 factors, the likeliness of unexpected behavior and then the cost to troubleshoot and repair the problems. So if I wanted to understand the things that were causing the pain, I needed to understand the things that caused these 2 factors. So I started breaking down all these problems into categories. And what I realized as I was doing this was most of the pain was actually caused by human factors. So for example, stale memory mistakes. This is when I have an idea in my head about how the code is supposed to work, but it doesn't work that way anymore because somebody changed it. Or ambiguous clues. This is when you're running an experiment and there's multiple possibilities for how a behavior can occur, and you make a bad assumption and down the troubleshooting rabbit hole you go. So neither of these are problems with the code itself. Pain is really a consequence of how we interact with the code. So pain occurs during this process of understanding and extending the software. So I started optimizing for what I call idea flow, or this flow of ideas between the developer and the software, rather than just optimizing the code in isolation. So after we started looking at the data, we started to realize on our project we'd been failing to improve because we weren't solving the right problems. We spent tons of time working on improvements that didn't actually make that much difference at all. And I learned one of the most valuable lessons of my career. The hard part isn't solving the problems, it's identifying the right problems to solve. So I started using these visualization tools on consulting projects as a way to help other teams identify their biggest problems. So in this first case study, there was this huge mess inherited by a great team. It was this 12-year-old project where all the original developers had left. And this is what it looks like when you spend 90% of your time figuring out what to do and 10% of your time actually changing the code. So this was the norm on the team, to spend 70 to 90% of the team's development capacity on friction. So there were tons of problems to solve, and the team wasn't really sure what to focus on. So they set a goal to raise unit test coverage by 5%. And then we started adding up all the problems across the team, and these guys were spending almost 700 hours a month generating test data to support whatever task they were working on. But oddly, in all the retrospective meetings they had, this problem didn't even come up. Like, people just considered it part of the normal work, and so they didn't think about it. So in this other case study, I was working with this team 18 months after they started this massive rewrite effort of their application. So they're going from a legacy hairball monolith application to a microservices platform, continuous delivery, the whole 9 yards. And what amazed me about this project was after only 18 months, they were already spending about 40 to 60% of their dev capacity troubleshooting problems. And I started working with this team just as they were getting into the thrashing stage. So I got to watch this team right at the tipping point, starting to lose control of their project. And I put together this chart using sample data, so I don't have quite enough data to do this, but you could see this long-term pattern that we always talk about in software of pain building up over time. So learning is front-loaded in the release, where the team is kind of figuring out what they're going to do. And then there's this rush before the deadline, where validation ends up deferred until the very end of the release. And then over time, the pain builds, and you can see this baseline friction level steadily rising. Then eventually chaos reigns, and the work stops fitting within the time box. So in this last release, I'm charting capacity hours over time. So you can actually see the developers had to work twice as many hours to get the release out the door, even though from a calendar time perspective, all these releases are the same size. So it's pretty awesome that we can see pain at this level, but we've still got another problem. So if you watch what happens right before a project crashes into the wall, everyone usually knows there's a problem. The engineers are like, we're going to crash. And management's like, what do I do? We can't miss these deadlines. Even when the pain is really obvious, we still get stuck in this pattern of organizational deadlock where nobody can change direction. And so we crash the car and have to build a whole new car just so we can continue driving. And the challenge with trying to steer an organization is that decision making in an organizational context is a distributed responsibility. So when I think about distributed decision making, I imagine, what if our organization was like a robot? And we've got the dev team controlling the hand component and management controlling the arm component. And if we run a little experiment and light a fire under the pain sensor, nothing happens. And if we turn up the fire, so we've got 10 times the pain, we burn. This is what happens when there's a broken feedback loop baked into the design of the system. If the feedback loop is broken, we burn. So if you think about the human system design kind of like a software design, you can see that the broken feedback loop is actually baked into the organization's role design. Whenever visibility and decision making are decoupled into different roles, communication failure leads to this crashing pattern. And when visibility and decision making are part of the same role, we can steer in response to emerging risks. So there's a couple different places that you see this pattern come up in our organizations. For example, the management role is responsible for allocating money and managing risk. And all the knowledge about technical risks on the projects are generally in the developers' heads. So communication breakdown at this level tends to lead to a whole lot of really bad risk management decisions. And another place you see this pattern is with the product owner role. And the product owner is in charge of making trade-off decisions about technical risks that they generally don't understand. So communication breakdown at this level leads to the classic case of technical debt building up on a project because the problems are constantly being deferred. So we can try and solve these problems by trying to find a way to communicate better. But we've got tons of evidence that says this strategy doesn't work very well. I mean, there's a reason the story I told about project failure is an archetype across our industry. This problem is baked into the blueprints that we're using to design our organizations. So I'm proposing we move to a model more like this, where we have a technical risk manager whose job it is to analyze the data, identify the biggest cause of pain, and then prioritize risk management work for the team. So if the hardest part of the job is identifying the right problems to solve, then understanding the problems ought to be someone's job. I mean, if we do a poor job of gathering product requirements, we build features that nobody wants. And if we don't understand the problems that we need to solve on the team, we also build improvements that are ineffective. It's pretty much the same thing. Requirements needs to be somebody's job. So this pattern, you notice that the knowledge and the decision making are coupled now in the same role, so this gives us the ability to steer. So if I go back to my robot metaphor, I'm repairing the broken feedback loop kind of like this. I've got an explicit pain sensor now attached to the engineering team, and I've got detailed data at the engineering level to make improvement decisions, and then management can use high-level summary data to make long-term risk management decisions, and then in the middle I've got this risk translator role supported by the technical risk manager who's responsible for translating all the problems happening in the weeds of software development into a language of high-level risks and costs that can be taken into account in management decisions. So Open Mastery Learning Framework is a strategy for repairing the broken feedback loop in our organizations. And with a data-driven feedback loop, we can use the scientific method for making better quality improvement decisions, and then create visibility for managers to make better quality investment decisions. So the learning framework becomes this high-level steering system for driving the entire organization from top to bottom with science. So that's the big picture of where we're headed. And Open Mastery is about learning our way there together. So if you want to join us, all you got to do is sign up.